Dear students, today we will be discussing about a numerical problems for your better understanding of design of a off-grid solar PV system. So, let us take a numerical problem. So, we are considering a typical house having following load requirements. We have lights, 3 lights of 25 watt compact fluorescent bulb, and we need to operate it daily, and it is a DC power supply we need, and night time 5 hours we are expected to operate this light, and one more light, it is rated at 11 watt compact fluorescent bulb, and we need to operate it daily, but it is a power requirement is AC type alternating current, and it is expected that it will operate for 5 hours. And water pump of rating 50 watt and 6 ampere is the start current, and we need daily, and power requirement is DC, and every day 2 hours it will be operated. And we have oven, its power rating is 500 watt 3 times a week, and requirement is AC, and daily daytime operation, and it will be 1.5 hours. Steam iron rating is 800 watt, once in a week this will be operated, and requirement is alternating current, and daytime 1.5 hours to be operated. So, you can see we have different power type, and we have few appliances having requirement in weekly basis, and others are on daily basis. Efficiencies and losses of various components of the systems are given, like inverter efficiency is 90%, battery is 75%, distribution circuit fuses wires is 95%, and PV array due to temperature derating is about 85%. We need to find out the average load and peak power to be satisfied by a PV system of 3.55 ampere rated peak current and 16.9 volt rated peak voltage at 60 watt with an inverter. Also, we need to estimate the daily energy requirement. The household needs battery storage, which is lead acid type. Normally in standalone system, lead acid batteries are used, and it is 12 volt DC at 100 ampere hour capacity, and we need 3 days autonomy. Maximum allowable depth of discharge for deep cycle battery is 50%, which is given to us. Again, we need to calculate the battery storage requirement, and we need to estimate the size of the PV array. So, all the components are included here. So, let us solve this problem step by step. So, now we have this appliances, light which is DC, then again one light is there which is AC, water pump is DC, oven is AC, and then steam iron is AC. And what is the power requirement is, here we have 3 lights and each of having 25 watt, right. So, this is like 75 watt, and here second light is in AC type. So, its rating is 11 watt. Okay. Water pump is DC, it is 50 watt, and oven is 500. So, it is what is that? Do not want that watt. The steam iron is 800 watt. Okay. Run time is how much? For DC lights it is for 5 hours, and for AC light again for 5 hours, and for water pump it is 2 hours, then oven 1.5 and steam iron is 1.5. So, energy requirement daily in watt hour. So, we have to multiply 75 multiplied by 5, then what we will get is something like 375, then 11 multiplied by 5 is 55, then 50 into 2 is 100, right, and these two are on weekly basis run. Okay. So, daily we will calculate later, first let us do the calculation on weekly basis. So, if we multiply with 7, then what will happen? What we will get is something like 2625 watt hour. Okay. And this is 385, this is 700, and here if we multiply for week, then how much it will be? 1.5 times, then 3 times in a week. This is 3 times in a week. So, it will be about 2250, and this will be 1200 once in a week, right. So, these are the weekly energy requirement, right. So, now we can calculate the average load, average DC load. So, this is DC and this is DC. So, it is 375 plus 100, this is 475 watt hour per day. Okay. And then we have average AC load, which will be equal to, so I will consider this part, last column, 385 plus 2250 plus 1200 divided by 7. So, it will be 547.9 watt hour per day. Okay. So, we have been asked to calculate two more parameters. It is peak DC load. So, how this can be calculated? So, if we see the problem statement, it is said for water pump starting current is 6 ampere and its voltage is 12 volt, and then in the first case it is 75 is the watt. So, if we do the calculation, it will be 147 watt. So, here 6 into 12, which is greater than 50 watt. This is 72, right? Is greater than 50 watt. So, 50 watt, if we see the problem statement, this 50 watt was the specification, but during starting it will draw more current. So, that is how this has to be accounted, and we can find out the peak DC load, right, which is found to be 147 watt. And also we can find out peak AC load, which is nothing but 11 plus 500 plus 800, which is equal to 1311 watt. Okay. So, this is the answer to the first question. Answer A. Now, let us do some kind of analysis. Say if we are interested about equivalent DC load. Okay. So, DC DDC equivalent. So, this will be something like DDC plus DAC, then inverter efficiency. Okay. Total equivalent load or say equivalent DC demand is something like, if we have DC and an AC, then we can make it equivalent by using the inverter efficiency. Okay. This is one case. Second case may be when the array supplies all energy to a DC load, then the actual energy delivered will be something like, we are representing E D DC, which is equal to E A, the distribution. So, this is something like losses associated with the cables. Okay. And maybe we can have more such kind of situations. So, when the battery directly supplies a DC load, the efficiency battery is represented by eta bet, then the actual energy delivered will be E D DC, then battery. This will be something like E A, this is the array, from array how much energy is going to the batteries, and then this is battery and then distribution. Okay. This is one. And maybe sometimes when the battery is used to supply energy to an AC load, then what will happen? When the battery used to supply to AC load, and also we need to include inverter efficiency, then energy delivered will be E D AC battery, then it will be E A multiplied by battery efficiency multiplied by inverter efficiency multiplied by distribution efficiency. Okay. And there might be one more case when the array supplies all energy to an AC load. Then the energy delivered will be E D AC E A inverter multiplied by distribution. Okay. This is how we can use those expression for calculation of actual energy delivered. Okay. This is also actual energy delivered, actual energy. Okay. So, this is something like we have this module or maybe arrays, sun is here and this is connected to something like this is batteries. Okay. There are very many batteries maybe, these are connected in series and parallel, and then we will have some DC load and we need inverter for AC load. Okay. Fine. So, here also we can have DC load. So, without battery also you can use DC load, and with batteries also you can use DC load. So, this is how we can think of while formulating these strategies for calculation of EA here. Okay. So, that is actual energy delivered by this module or arrays, right. Now, let us calculate the average or expected daily loads. So, what we have learned, like what is the average DC load based on our calculation, the average DC load was 475 watt hour and the average AC load was 547.9 watt hour, and if we total it, it will be 1022.9 watt hour. This is the total load, right. So, expected daily loads are daytime we have DC, that means directly this energy is coming from the solar array. So, it is 100 watt hour, that means I can write from PV system. Okay. In situation 2, that will be used in night DC, and daily load is 375 watt hour, and this is coming from battery. At 3 again we can use it at night, and this is AC and it was 55 watt hour, and this is also from battery. Daytime AC. Okay. So, we can directly use it without having any batteries. So, this is 492.9 watt hour. So, this is something like 2250, how we have calculated it, 1200 divided by 7. Okay. So, this is how it is calculated, and this is from PV system through the inverter. So, if you can visualize it, something like if you have modules, then some are going to battery. This is a battery bank BB. We have DC load, I have inverter, this is AC load, and from here also we have load, which is DC load. Okay. So, these are different situations. So, now we can find out how much total energy is required. So, our target is to find out the total PV energy required to meet the loads. Okay. So, number 1 is like E d DC is something like E A distribution. Okay. So, from here we can calculate what is E A in for the case 1. So, this is something like this part already we have calculated, this is something like E d DC. So, we can calculate E A for the case 1 or for the DC load. So, it is 100 divided by we have 0.95 is the efficiency of the distribution. So, this will be something like 105.3 watt hour. For case 2, so we can visualize an expression of something like VDC battery, it is coming from battery. So, it will be something like EA efficiency of the battery and then efficiency of the distribution, because cables will be there. So, that is how this has to be accounted. So, from here you can calculate what is EA for the second load, which will be used at night, and DC it will come from battery. Okay. This is something like 375 and then battery efficiency is 0.75 multiplied by distribution is 0.95. So, this will be 526.3 watt hour, and for third load it is at night. So, it will be E D, this will be AC, night at AC, and then this will come from battery. Okay. So, this will be something like EA, then we will have battery multiplied by inverter because it is AC, and then distribution will be there. So, we can find out what is EA here. So, EA is found to be 55 divided by, this is 55, and we will have all those efficiencies 0.75, inverter is of 90% and then distribution is 95. So, this is about 85.8 watt hour, and for this load is daytime is AC. So, it will be E D AC. So, it will be like E A multiplied by inverter efficiency multiplied by distribution efficiency. So, we can calculate what is E A here. It will be something like 492.9 divided by inverter efficiency is 0.9 divided by 0.95. So, this will be 576.5 watt hour. So, if we are interested for total PV energy required to meet the loads, then we have to add all those 4 components. So, if we add it, then what we will get is the expected daily energy requirement, expected daily energy requirement to meet the loads will be 105.3 plus 526.3 plus 85.8 plus we will have 576.5. So, this will be equal to 1293.9 watt hour. Fine. This is EA values. So, once we are done with this, then we can go for sizing of the battery. Okay. How we can think of battery storage requirement. So, battery storage requirement, now I will say battery so, this can be calculated by using the knowledge of battery specification and the value we have calculated just now. The total daily ampere hour requirement, which is equal to daily energy watt hour divided by system nominal voltage. So, total daily ampere hour will be 1293.9 divided by 12. So, this was watt hour, then divided by 12 volt, then this will be 107.8 ampere hour per day. Okay. So, battery bank capacity, what is the required battery bank capacity will be, you know, the days of autonomy, days of autonomy multiplied by daily load ampere hour divided by battery DOD multiplied by battery efficiency. Okay. So, can calculate 3 multiplied by, we have 107.8 divided by, we have 0.5 into 0.75. So, this will be 862.4 ampere hour. Right. So, sometimes we are also interested about average daily DOD, which is like total daily load ampere hour to the total battery bank capacity. So, it is something like 107.8 ampere hour to the 862.4 ampere hour, which is equal to 12.5% daily. Okay. So, if we have to find out the number of batteries to be connected in series and parallel, that also we can do it. So, number of batteries in series connection will be something like 12 volt is the total volt divided by 12 volt is the rating. So, this is 1 battery, and number of batteries in parallel will be, we know 862.4 is the required battery bank capacity to the individual battery capacity is 100. So, it will be 8.624, which is approximately equal to 9. Okay. So, 9 batteries. So, for battery we need to have 9 batteries which are to be connected in parallel, right. Now, next phase is PV array estimation. Let us do the PV array estimation now. So, here for this PV array estimation, what we need to do? We need to consider the minimum amount of solar radiation available. That means, which month this is minimum amount of solar radiation is available, that we need to find out, and how is daily load. So, for this we are considering the month December. It is expected that it will give about 5.4 hours of radiation, and we are considering the maximum load. Okay. These two conditions need to fulfill, and we have to consider total system loss or losses, which is 0.9, 0.7, 0.95, all the efficiencies including the temperature compensation. So, it will be about 55%. Okay. And what will be the adjusted load requirement? It is something like 107.8 ampere hour, this is days, divided by 0.55. So, it will be about 196 ampere hour per day. Okay. So, if we have to find out the number of modules to be connected in parallel, then how we can do it? We can have adjusted load ampere hour requirement to the module peak current output and peak sun hour. So, it will be 196 divided by 3.55, which is given to us, and 5.4 hour. So, this will give you the number of modules to be connected in parallel, which is equal to 10 modules. So, this is adjusted load requirements to the module peak current output and peak sun hours, right. So, this is one of the important findings, and secondly, number of modules to be connected in parallel, series. This will be like, we need to the nominal voltage of the system is 12 volt, to the module peak voltage output is 16.9 multiplied by voltage temperature D rate, which is about 0.85. So, this will give 0.84, which is equivalent to 1. Series. Okay. And you can verify our result as well. Total PV array will be 1 in series and 10 in parallel. So, here we have shown how a solar off-grid system can be designed. It includes all the aspects of battery, PV modules and the loads, kind of loads we have. We have also demonstrated how this load can be considered even though they are of different character. Okay. So, in nutshell, we have demonstrated the design with the help of a working example. I hope that you have got an overview of a solar PV off-grid design. Thank you very much for watching this video. Thank you.